So Bismillahir Rahmanir Rahim. Now we will discuss the concept of the weight of an object, and now we will try to understand what's the difference between the weight and the mass of the object. So weight. So for example, there is a person that is standing on the surface of the earth. So we have a person that is standing on the earth. For example, right now I'm standing on the earth, and because of the gravity, there is a gravitational force that is always there, as we have discussed this in our previous lectures. So we have gravitational force, which is equal to mg. So we have the gravitational force, and as we know that according to the Newton's second law of motion, if there is a force, there must be an acceleration here. So we have an acceleration that in this case, in the case of the gravitational force, is equal to the gravitational acceleration, and acceleration means that there will be a change in the velocity. But right now, for example, right now I'm standing on the surface of the earth and there is no acceleration, so that means that this force is cancelled by another force, and this force is in opposite direction here. So this force, which is in opposite direction, is known as the normal force, and this normal force is actually the weight of the object. So this normal force, as we can see here, this must be equal to the gravitational force, which is equal to mg. So we have the weight of the object. So the weight of the object in this case is the normal force, and that is equal to the gravitational force, which is equal to the mg, the mass into gravitational acceleration. What's the difference between the mass and the weight of the object? So the mass of the object is always the same. So it can never, we cannot change the mass of the object, whether we are on the surface of the earth or we are on the moon, for example. If a person is standing on a moon, then the weight of the object, weight of that person will be 6 times smaller than that of the earth, because the moon's gravity, the gravitational force, the gravitational attraction is 6 times smaller than that of the earth. So if the gravitational acceleration is 6 times smaller, then that means that the force, that the weight of that object, which is this normal force on the moon, will be 6 times smaller than that of the earth. But of course, this mass will always be the same. So that's the difference between the mass of the object and the weight of the object. And the mass, we measure it in terms of kilograms. That's the standard units. But since this is a force, the weight is the force, and the unit of the weight is actually newtons. So this is the force, and that is the difference between the weight and the mass of the object. And now we want to discuss some cases where we want to see if the weight of the object is changing or not. For example, we have a person that is standing in elevator. So we have a person that is standing in elevator. So that's the person here, and as we discussed here, there is a gravitational force on this object. To cancel this force, since the person is standing on the bottom or on the bottom surface of the elevator, and the elevator is going up. So this elevator in this case is going up. So this is the gravitational force, and to cancel this force, there will be another force, which is the normal force. And now, since this whole system is going up, means that there is an acceleration upwards. So that means that this normal force is bigger than the gravitational force. That's why the lift is going up, so the whole system is going up. And now we want to see what's the weight of this object, weight of this person in this case. As we see that this whole system is going up, so this force is bigger than the gravitational force. So F normal is greater than this one, so F normal minus mg. So the total force on this person is the F normal, which is the up force, which should be larger in this case than the gravitational force. So the total force on this object of this person is so this is the total force on this object. It must be equal to ma. So according to the Newton's second law of motion. So this is the total force equals to ma. And now we want to know what is this weight of this object, which is this normal force. So the normal force is equal to m. So if we move this one here, then we will see that we have the a plus g. So this is the acceleration direction of the acceleration that is moving up. So with the whole system is moving with this acceleration, so we have this acceleration is added to the weight of the object. So that's why when we are standing in the lift and the lift is going up, we actually our weight is increasing by the amount of the acceleration, which is when the elevator is moving up. And this elevator, the acceleration of the whole system is added to your weight. So this is what we feel. We feel heavier when the elevator is going up. And now we discuss a case where this acceleration here is downward. For example, the same elevator, we have a person standing in elevator. There is a gravitational force which is mg, and there is a normal force again to cancel this force. But this time the acceleration of the system, so the elevator is actually going down. So if the elevator is going down, that means in this case, since it is going down, that means that the downward force, which is the gravitational force, is dominant in this case. So we will write in this case that mg, the total force on the system, is minus F normal, which is the weight of the object. So again, this is the total force on the system, must be equal to, according to the Newton's second law, must be equal to the ma. And now if we rearrange this equation in order to get this weight of the object, so we will get normal force is equal to ma g minus a. So now what we see here, so this was the weight of the object or this person when this person was not moving, for example here in this case. But now since the elevator is going down, so we feel lighter when the elevator is going down. So by the amount of this the acceleration at which the elevator is going down. So that's why when we are standing in elevator and elevator is actually going down, so we feel that our weight is smaller. We feel of this small weight in this case. But now if this acceleration is equal to g, so this acceleration with which the elevator is going down, if this acceleration is equal to gravitational acceleration, which is equal to 9.8 meters per second squared. So that means if we put here in this equation, so the weight of the object in this case will be mg minus g. So g minus g is equal to 0. So the weight of the object will be 0. So this is, in this case is known as the free fall. So the free fall free fall is when the object is going down, and there is only one force that is acting. This only one force that is acting on the body is the gravitational force, and this force is zero because this object or the whole system is moving with mg. So there is the person is not feeling this normal force, so you will be feeling weightlessness. So the weight is zero, and this can be, you might have seen some videos on the internet where the aircraft is moving, so accelerating downwards with the g, which is 9.8 meters per second, and people in that aircraft are actually flying because there is this normal force is not there because the whole system is accelerated with the g. So in this case the weight of the object is zero, and this type of system where the downward acceleration is the whole system is g, so this is called the free fall. And the free fall, the only force that is acting on you is the gravitational force here, this force. So that if there is only this force, that means the acceleration is equal to g, and there is no this force. So so from this we can see that the weight of the object can vary. It depends in which direction the object is accelerated. If it's accelerated upwards, the weight of the object will be increased. If we are going down, if the system is accelerated downwards, then the weight of the object, which is in this case, will be smaller than the weight of the object in the static state, which when the object is not moving. But if the object is accelerated downwards with the acceleration which is equal to the gravitational acceleration, which is 9.8 meters per second, and in this case your weight will be zero, and this is called as the free fall. And now we discuss the escape velocity. So we have the escape velocity. So escape velocity is when we are, for example, on the surface of the Earth. So this is the Earth, and we have a radius of the Earth, which is we represent here in this case with the big R, and then we have the mass of the Earth with the big M. So we have the big M here, and there is a person who is standing on the surface of the Earth. So as we know that if we are on the surface of the Earth, we will feel the gravitational force because of the gravitational potential energy. So we have this gravitational force. But as we go away from the Earth, as we have this derived or discussed this in our previous lecture, that as we go away from the surface of the Earth, we're moving away from the Earth, the gravitational attraction will be getting smaller and smaller. So at certain point, if you are far away from the Earth, for example, this is the r small, this is the small r, so this is r is representing the distance from the surface of the Earth, from the surface, or from here, from the surface of the Earth. So if we are far away from the Earth, somewhere in the infinity is the place where the gravitational force due to the Earth's mass is almost zero. So that means if something is here, this will not feel this gravitational force, or the gravitational force will be negligibly small. So the escape velocity is that velocity. If we throw something, for example, if I throw something up, it will go down again because of the gravitational force. But if I throw something with initial velocity that reaches this point, for example, if reaches this point, at this point the object will not feel the gravitational force, so it will remain here. So we want to know what should be the minimum velocity that is required to reach this infinity point. So at this infinity point, so we want to know what initial velocity. So this is the velocity which is, we represent it by escape velocity, escape. So a velocity which is required to reach this infinity point. So at this infinity point, the kinetic energy will be 0 because it will stop at this point, and the potential energy will also be 0 because it's not feeling any gravitational force here. So we want to know, as we have derived this mechanical energy was equal to sum of the kinetic energy, so kinetic energy squared plus the potential energy. So we have the G and the R. So we have the R is here, the radius of the Earth. So the mass, small m, is the mass of this object, and the big mass, the big M here, is the mass of the Earth. And now we want to know what should be the velocity here, this escape velocity. As we know that the mechanical energy is always conserved, that we have already discussed in our previous lecture. So the mechanical energy, the total mechanical energy, which is the sum of the kinetic energy and the potential energy at this point, must be equal to the mechanical energy at this point. So we will use this conservation of the mechanical energy. So first we will write mv escape squared, the kinetic energy at this point. So the initial velocity here is the escape velocity. So we have written here the kinetic energy at the surface of the Earth, and it has the velocity which is the escape velocity, and the potential energy on the surface of the Earth. So this is on the surface of the Earth, the total mechanical energy, which must be equal to the kinetic energy here at infinity, so minus m g, and this is small r. So this is the, at big R means at here, so this is the, this side here, the left hand side, is the kinetic energy of this object here with the escape velocity. It has the escape velocity on the surface of the Earth, and this is the potential energy with the big R means only at this point. And now here, this is the kinetic energy at infinity. So if, as we said that when it reaches the infinity, the velocity here, this velocity will be getting smaller and smaller and smaller. For example, if I throw something up, the velocity will be smaller and smaller and smaller, and at some point it will stop and it will come back. But since it reaches the infinity, the velocity will be getting smaller and smaller and smaller. At the infinity, the velocity will be 0, but since there is no gravitational force at infinity, that's why it will stop there. So that's why this term is 0. Since we are at the infinity, so this infinity means that the downward, this R, is infinity, and the gravitational potential energy at the infinity is 0. So this term is 0. Now we want to know what is this kinetic energy. So this whole term on the right hand side is 0. So we just move this part there. So we can write 1/2 m escape velocity squared equals this m divided by r. And now we can easily write E as, so escape velocity is equal to 2 m g divided by or under the root. So this is the escape velocity. So now what we see here, we have the constant, we have the mass of the earth, we have the gravitational constant which is known, we have the radius of the earth. If we put these values here, we will get that this escape velocity is equal to 11.2 meters per second. So this 11.2 meters per second is the escape velocity for the earth, and this escape velocity, as we see here, so it depends on the mass of the earth, and if we throw something with the escape velocity, it will reach the infinity, it will never come back. And similarly, if we are on the surface of the moon, the escape velocity will be different. First of all, we have the mass of the moon is different from the mass of the earth, and similarly we have the radius of the moon is different from the radius of the earth. So if we know both of these, we can calculate also the escape velocity on the moon and also on the other planets. And this escape velocity is only valid if we ignore the atmosphere. Of course, if we have the atmosphere, Earth's atmosphere, as we will discuss in our next lecture in the fluid dynamics, if we are moving through the fluids, the air is also a fluid, we will feel a resistive force, and this resistive force will stop, it's a resistive force, it will, so this escape velocity will never be valid, and this will be lost. This escape velocity is only valid when we ignore the air drag and the drag forces here in this case. And now we discuss the orbital velocity. So the orbital velocity. So from the name itself, we have the orbit here, so there must be something orbit. So we have, for example, the Earth, and we have some satellites that are revolving around the Earth. So we have so this is the big mass here, mass of the Earth, and then it has a radius here, so radius here, and we have the small mass, so it can be a small artificial satellite, or for example we have the International Space Station or other small satellites that are revolving around the Earth. So it has some tangential velocity, and there is this centripetal force. In this case it must be equal to the gravitational force. So we have this orbit, which is we have this object, small object, which can be a satellite, or it can be a natural satellite, which is a moon, for example. It's revolving around the Earth, and we want to know that what should be the orbital velocity. At what is orbital velocity means the tangential velocity. The tangential velocity, in this case we want to know the magnitude of this velocity, because the direction is constantly changing. So in this case here it will be here, and this case it will be here, and this case and this will be here. So we have this discussed already. So we want to know what should be the magnitude of this velocity to keep this object in a certain orbit. Orbit means a circular path which has a constant radius here. So the radius of the orbit should not change, and it should move in the same orbit with the. So we want to know what should be that orbital velocity. So the big R is the radius of the orbit here. So we should not confuse it with the radius of the Earth, which we discussed this in our previous example, but in this case this is the radius of the orbit here. And the mass of the small object, the satellite, must be much smaller. So it's much. So the mass of the satellite must be very, very small compared to the mass of the Earth. But I have written it wrong. So the mass, the big mass must be replaced with the small mass in the case which is written on the board. Much smaller in this case, and we want to know what should be the orbital velocity. So if it's moving in the same orbit, so in this case, so the centripetal force. So since this is moving in a circular path in the orbit, so there is this centripetal force, and this centripetal force is constantly changing the direction of the velocity, and that's why it's moving in the orbit here. So this in this case it must be equal to the gravitational force. That's why it's not changing. It's in the constant orbit. And if the gravitational force is dominant, then it will be spiral towards the Earth. So we have discussed that the centripetal force is equal to mv squared divided by r, so the radius of the orbit, and it's equal to the gravitational potential energy or the gravitational force, which is equal to the mass of the Earth. The small mass is the mass of this object here. So radius square, so from this, so this is that is orbital velocity here. So this is the orbital velocity. If we move r here, it will cancel, and we have the small mass. For example, we lose the mass, and we lose the square here. So we will get, since this is a square, we will have the square root on the other side. So we have the big M divided by the r under the root. So this is the orbital velocity. And now what we see here, this orbital velocity depends on the distance from the Earth. So if we are far away from the Earth, the orbital velocity will be smaller. If you are close to the Earth, then the orbital velocity will be larger. Similarly, it depends on the mass of the Earth. So if the mass of this object, for example, if we are on the different planet, then the orbital velocities at the same distance will be different because they have the different masses here. And now we want to discuss an example of the moon, which is revolving around the Earth, and we want to know what is the orbital velocity of the moon. So we have, for example, the Earth here, and then we have the moon, which is revolving around the Earth. So this is the Earth, and then we have the small moon, which is revolving around the Earth. So we have this example, which is an Earth satellite, which is a moon, is in the circular orbit at the distance of 384,000 kilometers from the Earth's surface. So what is its period of one rotation, and also we want to know what is the velocity. So the r here is equal to, so we have the r is the radius of the Earth, and then we have the distance. So we have the r is the radius of the Earth plus the height. The height is the distance between the surface and the moon. So we know that the radius of the Earth is 64,000 kilometers, and plus the distance from the surface of the moon, surface of the Earth to the moon is the 384,000 kilometers. So this is equal to 3904. So this is in kilometers. So using this formula, if we put these values here, so we have the mass of the object, we have the radius of the object, so we can calculate the orbital velocity. So the orbital velocity, so we use the same formula, m divided by r. So we put this value, so this is the gravitational constant, this is the mass of the Earth, and this is the distance that we just calculated. If we put this value here, so the tangential velocity of the kilometers, 1.1 kilometers per second. So this is the tangential velocity of the moon in the orbit. For example, this is the tangential velocity. The moon is revolving around the earth with 1.1 kilometers per second. And now we have, since we have the speed and we have the radius, so from this, if we calculate the period of this satellite or the moon is 27.5 days, if we calculate this in terms of days. So the moon is actually revolving, around the earth. It completes one rotation around the earth in 27.5 days. So we can calculate it using these physics concepts. And now we want to discuss another example. We want to calculate the orbital velocity of the International Space Station. So as we have just calculated or derived the orbital velocity is equal to, so this is the radius of the orbit here. So we want to discuss the orbital velocity. We have, for example, the Earth, and then we have the space station, the International Space Station, which is revolving around the Earth. And this International Space Station is much closer to the Earth than the Moon. The Moon is far away from the Earth. And we want to know what's the orbital velocity in this case and what's the time period. So if we use the same, for example, this is the R here, for example, the R, big R. So the R is equal to, so this is the radius and this is the small. So this is the R is the, so the R is equal to radius of the Earth. So which is, we can say the big R, which is 6,400 kilometers plus 400 kilometers. So this is the distance between the Earth's surface and the International Space Station, which is around 400 kilometers away. So if we calculate, this is the sum is 6,800 kilometers. So this is the total 6,800 kilometer is from the center of the Earth. If we put these values here, so we have the mass of the Earth, we have the distance from the center of the Earth to the International Space Station, which is 6,800 kilometers. If we put these values, we will get the orbital velocity for the International Space Station, which is 8 kilometers per second, which is almost 8 times higher than the orbital velocity of the Moon, because the Moon is far away from the Earth than compared to the International Space Station. And the time period is equal to 90 minutes. So the International Space Station is completing one rotation around the Earth in 90 minutes, and for the Moon it was 27 days. So it depends on the distance from the Moon, from the Earth. So that's, we can see here, if we have the radius or the distance from the center of the Earth to the orbit is smaller, then we will have the higher velocity. So we have the higher velocity, and then we will have the small time period. So it will take, so we have the high velocity means it will take a small amount of time to complete one rotation. Similarly, so we have the, if we can calculate the same thing for the Earth and the Sun. So the Sun is actually the mass of the Sun is also known. So if you put these values, the mass of the Sun here, and then the radius or the distance between the Sun and the Earth, so we will calculate the velocity is 30 kilometers per second. So the Earth, for example, the Earth around the Sun is moving. So for example, this is the Sun and this is the Earth. So the Earth is moving with 330 kilometers per second. So this is for the Earth, and if you put the values here, you will easily find these values. If we form this velocity, orbital velocity, if we calculate the time period of the Earth, time period is when the Earth complete its once rotation, and that time period in terms of days is 365.5 days, which is the 1 year in this case. And now we want to discuss, since we are talking about the circular motions, so we want to come back to, or these were also the circular motions, so we want to talk about the kinetic energy of the disk. So a disk is something, for example, we have, okay, so we write the kinetic energy of rotating disk. So we have a rotating disk, for example, here, and this is revolving, so it is spinning like this. So we want to know what is the kinetic energy of this disk. So if it's not moving in a straight path, but it's spinning, so so this is the solid disk, for example, solid disk. So this is completely, this is a disk, for example, and this is the center of this rotation, axis of rotation, it's spinning, and we want to know what is the kinetic energy of this disk. So to calculate the kinetic energy of this disk, so we want to just divide this disk into small pieces. So this is a small piece, so we just call it Mi. So Mi is one small element of the mass here, and it has it's the complete mass, but we take a small element, and we want to know what is the kinetic energy of this small mass. And then when we know the kinetic energy of this small mass, and then we add up all the mass of the disk, then this way we will know what is the kinetic energy of this disk. So the kinetic energy of the small element there is kinetic energy of the small element I here, that small element here, is 1/2 MIVI squared. So the velocity, tangential velocity, for example, here in this case is here, but at the other moment in time it will be changing here. So this is the VI here. So this is the kinetic energy of this small element here in the terms of this small element. And now, since we know that, as we come close to the center, the tangential velocity is actually getting smaller and smaller. So here, if you are far away, the tangential velocity is very high, but if we are at the center, if somebody is standing on the central point of a disk, so if it's rotating like this, so the tangential velocity here is 0. So the tangential velocity depends that how far you are from the center. But if we take the angular velocity, angular speed means that how many times you are rotating. The angular speed is the same because the angular speed is how many times it's spinning in 1 minute. So that's the same for this point and this point and this point, but the tangential velocity depends on the radius. So in this case, so we will take the angular speed instead of the tangential speed in order to calculate the kinetic energy of this disk. So we know that the tangential velocity is equal to the omega r, and this omega is the angular speed, and we can see here that this tangential speed here, tangential velocity, depends on r. So we will use this here, and then we put this v in this kinetic energy here. So we have the kinetic energy of this element, is m1 over 2 m omega squared, because we have r square, we have this v square, r square, and we do not have to write this I because the angular speed is the same for all these elements. So since this is constant for all the elements, so now we can write the kinetic energy. So the kinetic energy for the disk is equal to omega squared. So this omega squared, we can just take it out because this is constant for all the mass elements, divided by 2. So we have this divided by 2 in the downstairs here, and then the sum of all the elements here. So starting from E, from 1, and then we write the I R1. And this here, this term is known as the moment of inertia. So the moment of inertia is represented by I. So if we replace the moment of inertia here, so we will get the kinetic energy of the disk is equal to 1 over 2. So we have the 1 over 2 omega squared I. So this is the kinetic energy of the rotating disk. So what we see here, if we take the kinetic energy of the linear object, means if we use this tangential velocity, so we can compare it with the kinetic energy is equal to 1 by 2 m v squared. If we compare this equation with this one, we can see some parallels here. We have 1 by 2 here, we have 1 by 2 here, we have I here, we have mass here. So in the rotating objects, we have the moment of inertia. So the moment of inertia in the rotating or the rotational objects, it's same as the mass of the object. So if we have higher mass, so it will be difficult to increase the velocity or to accelerate something. Similarly, if the moment of inertia is higher, then it's difficult to accelerate something in the rotational things here. And then we have the v square here, which is the tangential or the straight velocity, and here we have the orbital speed here. And now this moment of inertia depends on first of all the shape of the object and the axis of rotation. For example, we have here this is the marker here, but its shape is like a cylinder. If this marker is spinning like this, so this is the axis of rotation. So in this case, the moment of inertia is smaller. But if it's rotating like this, then the moment of inertia is different because the axis of rotation is different than the previous case. So it depends on the shape of the object and also the axis of rotation. So for the solid sphere, for example, we have a solid sphere. So we have a solid sphere, for example, we have this radius of the sphere, we have a radius of the sphere, and then the axis of rotation is like this. For example, this is omega, and then we have the mass of the sphere. So the moment of inertia for the solid sphere is equal to 2 by 5 m r squared. The r is the radius of the sphere. But this moment of inertia is always different for all the different objects. Also in which direction or what is the axis of rotation, it depends on the shape and also the axis of rotation. So since we discussed now the kinetic energy of the rotating disk, since this is the form of energy and we want to know if this kinetic energy of the rotating objects or a disk can be converted to other forms of energies. So for that we need to discuss an example of an object. that object name is flywheel. So the flywheel is that object. For example, we have a disk, the same disk, and it's spinning like this. So if it's moving very fast, then that means that its kinetic energy is very high. And if it's moving, so we can see here from this. So from this equation, so if the omega is high, the kinetic energy is high. If the mass or the moment of inertia, which also depends on the axis and also the mass and the shape of the object. But here, if we look at this part here, if it's moving very fast, means it's spinning very fast, then it will have the higher kinetic energy. And we want to know that if we can store some kind of energy in the disk, rotating disk. So this is the omega. So omega, so it's spinning like this. So if we want to know if the kinetic energy of the spinning disk can be converted to other forms of energy, or if there is any way we can harvest this energy. So for example, to explain this, we have, for example, a mountain. So this is the surface of the earth. So this is the surface of the earth. So this is the surface of the earth, and this is the top height of the mountain here. So the height here is equal to 500 meters, which is the half kilometer. So if there is a car, that's on top of the of this mountain, and that car is coming toward the surface of the earth on a road which is looking like this. So we have a car which has some potential energy. We know that the potential energy is equal to, so the potential energy is equal to mgh. So we have a car which has a mass of 1000 kilograms. So we have a car, for example, here, so which has a mass of 1000 kilograms, and it's trying to come to the surface of the earth, but the car is usually moving with a very slow speeds, because it's not a good idea to drive with the high speeds on such a roads here. And we want to know, and to keep that small velocity, the driver has to apply brakes constantly all the time in order to reduce the speed of the car. So the speed of the car all the time is 4 meters per second, meters per second, so which is very small speed here, 4 meters per second. And if we calculate the potential energy of this car at the top of the mountain here, which is 500 meters above the surface of the earth, so this kinetic energy is equal to 5 into 10 raised to the power 6 joules here. So if you put the mass of the object, we have the gravitational acceleration, and we have the g, we have the h here, which is the kinetic, which is the height of this mountain. So if so we have the potential energy here, as we discussed in our previous lectures, that the mechanical energy is always conserved. So the potential energy can be converted to kinetic energy, but in this case we are losing energy because the driver is constantly applying brakes. So when the car reaches here at the surface, it has the same low speed, because the driver is constantly applying the brake, and that energy is converted to heat, and with this energy you can actually damaging your brake system and also your tires. So at this point, this kinetic energy with the 4 meters per second, if we calculate it, so the kinetic energy will be 1 by 2 mv squared, which is 4 meters per second, and we have 1000 kilograms, will be 8000 joules. So there is a huge difference between the potential energy. We have a huge potential energy at the top of the mountain, and then we have the small kinetic energy at the top, at the bottom of the. So we want to know if we can save, or we can convert or store this potential energy in a rotating disk so that we can use it later. So if we install a rotating disk, in this car, so instead of losing that energy in the form of heat, that will increase the speed of this, or the angular speed of this disk, which is installed in the car. So this way we can convert this potential energy into the kinetic energy of this disk, which is known as the flywheel. So for example, the radius of this disk is 0.5 meters, so which is like this much big, and we install this disk in a car, and it's spinning. If you wanna convert all of this energy to this the kinetic energy of this disk, then so if you want to convert, if you want to store this potential energy of this object which is on the top of the mountain here, so in this flywheel, so we know that we have the potential kinetic energy of the disk. So this disk is equal to 1/2 omega squared I. So for the disk we have the omega is equal to 1/2 m r squared. In this case it will be 2.525 kilograms meter here. So if we calculate, so if we transfer or store this energy, so what angular speed should we get? So if we calculate it, we will have the omega will be 632 radians per second, and the frequency will be 100 hertz. So the flywheel, if we install the flywheel in a car in order to store this potential energy which is at the top of the mountain, so if we do not have this flywheel, so we will lose all the energy by applying a brakes, and that will be converted to heat, and this way we will damage our tires and we will also damage our brakes. But if we instead install this flywheel which is spinning here, so as we apply the brake, instead of losing that energy in the form of heat, we will increase the speed, the angular speed of this flywheel, and all the energy will be stored in this rotating disk. And later this kinetic energy of this disk can be converted to electricity, because the car also needs electricity, and it can also be later converted to a mechanical energy, which can be used to accelerate a car.